Hi there, my name is Eric Newland. I'm a third-year PhD student at the University of Cambridge in the Department of Earth Science, studying in the BP Institute under the supervision of Professor Andrew Woods. And I'm here today to talk about the dynamics of deep submarine explosive eruptions. Explosive eruptions are known to have occurred in many submarine environments over geological history, and the associated deposits suggest that the eruption of fragmented mixtures of magma form ascending flows, which eventually feed submarine flow and fall deposits. Important examples include the deposits found on the Gackle Ridge in the Arctic, the well-documented deposits of the 2012 eruption of the Harvey volcano, and the Marsilli seamount in Italy. So, although the dynamics of the eruptions on the seabed and the associated fragmentation processes are poorly understood, these deposits are evidence of highly fragmented magma issuing from deep submarine eruptions, and these eruptions lead to deposits distributed kilometers on the seafloor. So these observations lead to two main research questions. The first being, how does the initial eruption column evolve as it rises through the water column? And secondly, how does the initial flow feed the distal fall and flow deposits observed? So focusing in on our first question. To investigate this, we're going to build a model for the initial eruption column. And to do this, we'll consider a mass flux of erupted fragmented magma Qm with a temperature T0, which mixes with a mass of seawater Qw to form a mixture of pyroclast and seawater with a bulk temperature T. To estimate the temperature of the mixture, we assume there's good thermal contact between the magma and seawater and use the equation for a conservation of heat, where L is latent heat of the magma, Cpm is the specific heat of the magma, and Hw is the enthalpy of the water. We also assume that the mixture cools below the solidification temperature of the molten magma, and therefore the density of the water-magma mixture is given by this equation, where ρm is the average density of the magma, and ρw is the density of the hot water. To estimate the density of the hot water as a function of pressure and temperature, we follow the values in the steam tables. And these account for the change in phase from liquid water to vapor at high temperatures and varying pressures. So we've coupled the above model for the heat transfer for a model of a buoyant jet, as given by the classical relations for Q, the mass flux, and M, the momentum flux of the mixture. This is where U is the horizontally average vertical speed, B is the radius, and rho is the bulk density of the jet. So we've solved these equations numerically for the motion of the jet. And here I present the density difference between the ambient water column and the mixture, and that's in the red line, and the temperature of the mixture in the black line. From this model, we can take away three key points. So the first being that as the water is mixed into the fountain, the water is heated to very high temperatures and expands to very low density. And this leads to the bulk flow becoming buoyant relative to the seawater. Secondly, after about 20 meters from the vent, sufficient mass of water has been entrained so that the mixture is now cooler and the water density has increased, so that bulk density becomes greater than that of the surrounding water. The flow then evolves as a negatively buoyant fountain that consists of dense pyroclast and positively buoyant warm water. You can see from this graph that it only rises 100 or so meters into the water column. Finally, if we implement this model for a number of different source conditions, we show that this maximum height is sensitive to the initial speed of the flow and the depth of the water. However, for all of these scenarios, the fountain still only rises at the maximum a few hundred meters into the water column. So this analysis has shown that from eruption of hot fragmented magma into the water column, a dense fountain of pyroclast and warm water may form and rise only a few hundred meters into the water column. Focusing in on our second question, then, how does the initial flow feed distal fall and flow deposits? To do this, we've carried out a series of analog experiments in which we form small-scale particle fountains by injecting a mixture of monodispersed silicon carbide particles into a density stratified saline solution. A series of images on the right show a time evolution of a typical experiment. In the first frame, you can see that the dense fountain rises from the source and reaches a maximum height h1, which is limited by the negative buoyancy of the mixture. Then, some of the fluid particle mixture collapses to the base of the tank, forming a radially spreading gravity current. Simultaneously, There is sedimentation of some particles at the top of the fountain. This may reduce the bulk density of the mixture, so it's now less dense than the surrounding fluid. The remaining particle fluid mixture may then rise as a buoyant plume through the ambient. The plume then rises through the ambient, stratified ambient environment and reaches a maximum height H2, where it intrudes and spreads radially. At this point, some of the particles sediment from the intrusion. So these experiments show that there may be two primary methods of deposition from a low-rising dense fountain. We have the flow deposit, which forms as a result of the collapsing fountain and the gravity current spreading along the base of the tank, and a fall deposit, which forms as a result of a buoyant plume rising and intruding into the ambient and particles sedimenting from the intrusion. So having identified the two primary modes of deposition, it's of interest to estimate the dispersal distance from such deposits. So first we'll consider the flow deposit formed as a result of the collapse of the eruption column. And to do so, we must first estimate the source conditions of the flow. We can approximate the volume and buoyancy flux of the flow using the values obtained at the top of the fountain from the initial eruption column. We must also consider the evolution of the particle concentration within the gravity current. These gravity currents can have complex structures and that may become vertically stratified. And once most of the particles sediment settled from this flow, the residual fluid particle mixture may undergo a buoyancy reversal and lift off from the sea floor, which may result in a reduced runoff distance. So noting these complexities, it's valuable to develop a simple estimate for the runoff distances of such currents. And therefore, we have an idealized model in which we assume the flow remains well mixed, and in which the particles sediment from the flow at settling speed, Vs, as it spreads radially. Here I present an estimate for the length scale over which the concentration of particles, and hence the deposition rate, drops to a factor 1/e and 1/e cubed of the initial value of the pyroclastic flow. This is for a particle settling speed of 1 centimeter per second. And you can see that the runout distance reaches 1 to 4 kilometers for the mass flux as shown. Next, we'll consider the fall deposit that forms as a result of particle sedimentation from the upper intrusion. To do so, we must first estimate the source conditions of the plume, and we can approximate the volume and buoyancy flux of the flow at the top of the fountain from the initial eruption column. We also find that for typical parameters of submarine eruptions, a fraction of about 0.8 to 0.85 of the particles settle from the flow, and the remaining fluid will become buoyant and rise as a plume. Therefore, to proceed, we assume that a fraction of fluid rises from the top of the fountain, carrying a fraction 0.1 of the particle load and forms a buoyant plume. The motion of this plume can then be described by the earlier model equations. We conducted a parameter study to explore the sensitivity of the model predictions and have found that when a fraction of 0.25 and 0.75 of the fountain fluid rises to form the plume, it can typically reach 100 to 300 meters above the fountain. So on reaching this maximum height, the fluid in the plume then spreads laterally in the ambient fluid, forming a radial intrusion. As the flow spreads radially, the particles gradually sediment from the flow, and the typical length scale of sedimentation from the spreading flow is given by the balance of radial advection of the particles and sedimentation. It's seen that this leads to dispersal distances of 1 to 7 kilometers for the mass eruption rate shown in the graph. In this figure, we've also added the region which corresponds to the deposits of the Gackle Ridge and Harbour eruption. And this data suggests that both of these eruptions are characterized by at least a minimum eruption rate of 10 to the 7 kilograms per second. So to conclude, the observed deposits give clear evidence of deep submarine explosive eruptions that feed both distal fall and flow deposits spreading kilometers over the sea floor. Our analysis of the initial eruption column shows that the eruption of fragmented magma may lead to the formation of a low-rising dense fountain. And from our experiments, we have identified that due to particle sedimentation at the top of the low-rising fountain, both fall and flow deposits can be formed. And finally, our model indicates that these deposits may disperse kilometers away from the vent. And thank you very much for listening.